Today I'd like to talk about the row and column spaces of a matrix. So what those are, how to find them, and that also naturally leads into the rank of a matrix. So we'll start with the definitions. Let me use my highlighter. Our first definition is the row space of a matrix, and it's just the span, which is something we've talked a lot about, of the set of rows. So whatever you can make using linear combinations of the rows, that's called the row space. And associated with that is a number, which is the row rank, which is the dimension of the row space. How many linearly independent rows you have, basically. On the flip side, we also have the column space, which is the span of the columns. Remember, the columns go this way and the rows go this way. And the associated number that goes with the column space is the column rank, which again is just counting the number of linearly independent columns, otherwise known as the dimension of the column space. Now it turns out that the row rank and column rank are the same. That's a theorem. And so we can in good faith make the definition that the rank of a matrix is that number, the row rank or the column rank, because that's the same number. So we can count it using either direction, horizontal or vertical, and get the same number, and we call that the rank. So here's an example to show what we mean by the column space. So the question is to decide if the vector 1, 3 is in the column space of the matrix 1, 1, 1, 1. Okay, so remember what column space means. It means in the linear span of the columns. So I think of making a linear combination of the columns, A times the vector 1, 1, B times the vector 1, 1. These are these vertical 1, 1s that I'm using here. And if 1, 3 is a linear combination of 1, 1, and 1, 1, it would mean that there exist real numbers A and B that would make this equation true. Well, this vector equation is really secretly two linear equations. So I can write down sort of the first coordinates give me A plus B equals 1. A times 1 plus B times 1 equals this one. And then the bottom row gives me A times 1, or in other words A, B times 1, or in other words B, equals 3. So that's my second equation. And whatever the real numbers A and B are, if they add up to 1, they're not going to add up to 3, right? Because A plus B is going to add up to a certain specific number. It can't add up to two different things. So I conclude that there are no solutions. Therefore, the vector 1, 3 is not in the column space. Let's try another example. A little bit bigger this time, 3 by 3. Let's decide if the vector 1, 0, 0 is in the column space of the matrix. Given here, I won't read off all the numbers. But it's the same idea, right? 1, 0, 0 is in the column space if I can find, and I use the letters X, Y, Z this time. So I need to find X, Y, and Z so that X times this vector, Y times this vector, plus Z times this vector turns out to be 1, 0, 0. I could write that as a system of linear equations, but I went straight to the matrix form. Right? For example, the first equation would be X plus 3Y plus Z equals 1, right? Kind of reading the top things. And then I'd pull off the coefficients 1, 3, 1. And then the other side of the equation is 1. A lot of times people put dotted lines in these matrices like that. So I've written the matrix that corresponds to the system of linear equations. And then I just row reduced it. And got this simpler matrix. And from this matrix, I can conclude that a solution exists. I can find an X, Y, and a Z, which tells me that yes, 1, 0, 0 is in the column space. If you're wondering how I'm seeing that a solution exists, I'm basically, okay, remember I have sort of a dotted line here, thinking about how do I turn this back into equations. And so my first equation is x equals 1/3, second equation y equals 5/18, and third equation z equals -1/6. So there's my solution. So it definitely exists right there. Okay, now it's time for another definition. This one, it's called the transpose of a matrix. And you get the transpose of a matrix basically by switching the role of rows and columns. So it says here, the column J of matrix A becomes row J of A transpose, or also called A to the upper T. This is the more common notation. So you're basically, whatever was your first row becomes your first column, whatever was your second row becomes your second column, and so on. In the next example, we'll have this come up, so I'll show you an example of it then. Okay, but first I need to tell you the methods, because allegedly this is a video about not real rank, sorry, my research is creeping in there, column rank and row rank, right? So how do you find a basis for the row space, for example, so that you know what the dimension of the row space is? So here we go. Okay, to find a basis for the row space, what are we gonna do? We're gonna do Gauss's method, that's row reduction. Until you get to row echelon form. You don't need reduced row echelon form. Regular row echelon form is fine here. And whatever you have that are non-zero rows, that's your basis. Okay, not too hard there. All right, what are we going to do about a column space? All right, so here's the method to find the column space. And there's actually two good ways to do this. So here I call this method 1. And this method, it starts out the same. Do Gauss's method, aka row reduction, until you get to row echelon form. And then you're going to look for the pivot columns, the columns that like start with a number that's not, so when you find a row and it's like, you know, when you have your echelon form, it kind of looks like this. Then the places where you actually have like your ones or your two, whatever your leading entries are, those are your pivot columns. Okay, so you find your pivot columns, and then don't take anything out of the reduced matrix. Go back to the corresponding columns of the original matrix, and those are your bases. All right, so that's one way you can find the basis for the column space. An alternate way you can do it, so here we are, basis for the column spacing, but now method 2, is using the transpose of the matrix. So you'll transpose your matrix, kind of do a flipping thing, do your row reduction on the transpose matrix, and then transpose back and just take the non-zero columns from that. So in some sense, you are now taking elements of the reduced matrix, but the transpose of the reduced matrix. Okay, let's see how this works. All right, so here's our task. Find a basis for the column space of this matrix A, reading across 1, 3, 7, 2, 3, 8, 0, 1, 2, 4, 0, 4. Okay, so I'm going to use method 2. Okay, so the first thing I did is I took the transpose of matrix. So to help you see that. Okay, so I took this row here. First row became the first column. Second row became the second column, and so on. So that's the transpose business. Okay, the second step in method 2 is to row reduce. So I just went to row echelon form. I didn't go all the way to reduced. Did I? Maybe I did. It doesn't really matter. You can use either. Okay, so now I've got this reduced matrix form. I'm going to give this a name. I'm going to call it B, just so I can talk about it better. Okay, and I'm going to take the transpose of B. So kind of same idea as before when I was transposing. I took this first row. Whoops, hold my highlighter. Try and keep my, here, I'll use different colors. Take my first row. Whoa, that's too dark. The first row becomes my first column. Second row becomes my second column, and so on. Okay, then what am I supposed to do now that I've transposed back is the non-zero columns become my basis. Let me write that over here. So what's the basis for the column space? 1, 0, 2/3 minus 4, comma, 0, 1 minus 1/3, 4. Just like that. Okay. And the last thing I want to talk about is why do we even care about column spaces? Is this just like a thing the mathematicians made up because we could? Well, not this time. It's actually related back to one of our sort of original topics in linear algebra, solving systems of linear equations. So, for example, let's consider a system of linear equations. I've got three unknowns, C1, C2, and C3, and then I've got my constants on the other side, which are not specified in this case, because I want to talk about it sort of more generally rather than a specific system. It's a sort of a family of systems. Okay. So this system has a solution if and only if the vectors of D's can actually be made as a linear combination of whatever column vectors I would need that correspond to my C's. In other words, if I wrote this in sort of vector form, let me uncircle this kind of in the way. Right, what are the coefficients on the C1s? 1, 2, 0, and 4. What are the coefficients on C2? 3, 3, 1, 0. And the coefficients on C3 are 7, 8, 2, and 4. So those are there. Okay. So if somebody gave me some specific D values, then there's a solution only if I can find C's that actually work to make this happen. Which is another way of saying, sorry, my picture's in the way, that the vector of the D's is in the column space of the matrix that corresponds to these vectors, which is exactly the matrix that we saw in the previous problem. If you kind of lump these three together, and it gives you this 1, 2, 0, 4, 3, 3, 1, 0, 7, 8, 2, 4. So for which D's is there actually a solution to this system? Only the ones that are in the span of those two basis vectors we identified on the previous slide. So that's everything I want to say about column spaces, row spaces, and ranks. Thanks for listening.